In a previous video, we talked about the possibility of traveling the galaxy, traveling to the center of the galaxy. Our motivation for this was the twin paradox. Once we understood a little bit more the fact that the person on the rocket traveling, if they traveled, say, to the center of the galaxy and then back again, they could end up actually making the trip in a reasonable amount of time, a number of years, and whereas when they got back, the time that had elapsed on Earth, say, was many thousands of years. But at least it opened up the possibility of making a trip and, in a sense, traveling forward into time when you get back, but certainly during the trip itself, your clock would just tick away normally, and you would live normally as you could expect, perhaps in a situation like that, and make it back in a lifetime. And then in the previous video clip, we talked about E equals mc squared and a few ideas of the concepts of energy. So now we're in a position to talk a little bit more about traveling the galaxy, because we mentioned that the practical limit, unfortunately, is just how do you actually get the fuel you need, how do you propel your vehicle so that you can get it up to the speed of light, say, or very close to the speed of light, not actually to the speed of light, because as you get closer and closer to the speed of light, it turns out that the energy you need goes up and up and up. But you can actually do some calculations. We're not going to do these calculations. I just written some of the key equations up here for those of you who've had some math to get a sense of what's involved in this. Essentially, we're doing a relativistic rocket problem for an acceleration of 1g, 1g being the acceleration due to gravity on Earth, 9.8 meters per second squared, as we mentioned before, or about 10 meters per second squared. And so you get equations like this relating the time passing on Earth versus the time passing on the rocket, where you talk about these hyperbolic trigonometric functions, where sinh of h, sinh of this value is defined to be e to the x minus e to the minus x over 2, and so on and so forth. You have another equation for the distance traveled. You have an equation for the velocity, because, of course, the velocity is changing. It's not constant velocity motion anymore, but we have acceleration, and so on and so forth. So it gets a little complicated there. But let's look at the results. And so this is a situation where the rocket is traveling a certain distance, and we also want it to slow down so we can actually stop at the other end and then maybe come back the other direction. So we want to figure out, okay, how long would it actually take to get a certain distance throughout the galaxy, and assuming we're going to actually stop at the other end, look around, take a few pictures, and then head back again, perhaps. So you work out those equations. Distance of 4.3 light years, essentially to the nearest star. The time on the rocket, which is the important value for our purposes to see if we can live that long, is 3.6 years. So not too bad. Just, we talked about a 1g acceleration. We showed that you can actually get up to very high speeds in a very simple, even simplistic calculation over the course of 300 to 400 days even. So in 3.6 years, you can accelerate up to speeds where you can actually get to a nearby star system. What type of fuel might you need to do that? Well, first of all, we have to figure out what fuel are we going to use. We talked about nuclear fission and nuclear fusion, and the fact that essentially what's going on there is you're turning matter into energy. In actual fact, you're not turning much matter into energy at all. In fusion, as we mentioned, you're taking two hydrogen nuclei, fusing them together, and essentially getting a helium nucleus out of it. And because the helium nucleus actually has less matter in it than the two hydrogen together, if you look at the mass involved, then the missing mass turns into energy. And so actually you don't have much missing mass in that process, but because of the E equals mc squared factor, that c squared value is so large, a little bit of mass turns into a lot of energy. And so maybe we could do something with nuclear fusion, but that's not very efficient, because even though you're getting a lot of energy out, you still have a lot of mass left over. And nuclear fission is even less efficient than that. So what we're going to imagine here is we're going to imagine a fuel that's 100% efficient. And the only situation we have with that is if you have a matter and antimatter collision, essentially, and the mass disappears and it turns into pure energy. For example, if you have an electron and the antimatter relation of an electron, the other particle, the antimatter partner, as it were, is a positron. And for whatever reason, the universe has a lot more matter than antimatter. In fact, that's a big puzzle that scientists have various theories about how that could have happened. Why is this great asymmetry, this great unbalance between the amount of matter, as far as we can tell in the universe, and the amount of antimatter, as we call it. But anyway, we can actually create antimatter. You can imagine electrons and positrons, bring them together. You turn mass completely 100% into energy. So that's the type of fuel we're imagining here. So we want to figure out, okay, given that we have enough of this stuff around and we can actually control it, how much of that would we actually have to take to fuel our rocket and get to, say, a nearby star system in 3.6 years? Turns out, not too bad, actually. About 38 kilograms. Now, the other thing we have to think about here is that a lot of this fuel is just going to propel the fuel itself, because the more fuel you add, the more mass you have, the more fuel you need to get going fast enough. So the more fuel we have here, the more fuel we're going to have to add on top of that just to get us going any place. That's one reason why the original Apollo rockets were so massive, the first stages, because you need to have a lot of fuel just to eventually get that tiny little capsule on top going toward the moon. So 38 kilograms, that's not much though, not too bad. Of course, a lot of technical details to overcome, technical hurdles to overcome to actually do that, but in principle, it's possible. What about if we wanted to go 27 light years to, it's actually the Vega star system is nearby. We can get there in 6.6 years. So a major star system, not too far away from us, relatively speaking, in terms of the galaxy. 6.6 years to get there, not too bad. How much fuel do we need then? Okay, remember, we're slowing down as we get there. So that's going to add to our fuel consumption, actually. And it turns out it's about 890 or so kilograms. So a fairly big jump there. But again, sort of, we can imagine that. What if we wanted to go to the center of the galaxy? Because that's the example we did before. And with the numbers we have here, 1g acceleration, it'd take about 20 years. Again, not too bad. We could imagine something like that. But now look at the amount of fuel we'd need to do that. Again, assuming a pure matter, antimatter rocket engine that was 100% efficient of turning all our fuel into pure energy that could propel the rocket. It comes out to be about 950,000 tons of material there, roughly speaking. So, I mean, that's huge, right? To even get that amount together, but then actually build a ship that could contain it. And then just for interest, we could even imagine traveling to another galaxy, the Andromeda Galaxy, nearby galaxy, relatively nearby, 2 million light years away. The relativistic analysis says we could actually get there in 28 years with a 1g acceleration. But again, that assumes we can keep that 1g acceleration going. And as we get faster and faster, closer and closer to the speed of light, it gets harder and harder to keep up that acceleration. And so in this case, we need about 4,000 million tons of the material. So again, we can see they're real practical, even in this somewhat fanciful situation where we have this super efficient, 100% efficient matter, antimatter engine. Even there, just trying to get the fuel for something like that is going to be a relatively impossible task there. Now, of course, we can think of other more science fiction type of solutions to this, things like warp drives, or actually even coming up with some way to manipulate the curvature of space. The general theory of relativity shows, at least in principle, that if we could do that, we could actually travel far distances in a relatively short amount of time with not much energy expenditure. But again, those are more science fiction at this point than anything else. So even though the theory of relativity holds out hope that, yes, we could actually travel these long distances in a short amount of time in terms of the time elapsed on the rocket, that unfortunately it's going to be a long time, if ever, that we're able to do such things.